New pictures gained by the James Webb Space Telescope have staggered experts. Instead of extending our perspective on the universe, these photos uncovered a disturbing reality. Our steady appreciation is lacking in making sense of the potential results of the universe in its early phases, where the theory of the Big Bang appears to reach its limits. This drives us to consider new speculations regarding its origins. The inquiry arises: how is the universe shaped? And why does this new transparency challenge even the most experienced experts to understand more about the Big Bang and the intricate details of this discovery? Shouldn't we examine the possibility of the Big Bang itself? Ignoring standard thinking, the Big Bang was not an explosion in pre-existing space. Perhaps it was space itself that began around 13.8 billion years ago, alongside matter and time. An anomaly in physics and cosmology describes places where gravity is so extreme that the curvature of spacetime becomes infinite. Today, following billions of years since the beginning of the universe, we see that our vast home is part of a grand cycle. For experts, this represents a fundamental piece of the universe because its very existence is clearly a continuous progression. However, it's important to understand that the universe isn't floating into pre-existing space. Rather, space itself is constantly expanding in size. As demonstrated by current theory, the first stars began to shine somewhere between 200 to 300 million years after the Big Bang, marking the end of the so-called Dark Ages. This was the point when the first bright, luminous objects came together to form mature systems. However, the speed at which these vast systems formed remains a perplexing mystery. A wealth of information emerged through the first images captured by the James Webb Space Telescope in July 2022. Experts revealed that the telescope had detected intriguing cosmic systems, some of which had already existed around 300 million years after the universe's formation. However, unlike the massive permanent structures that formed much later, these early galaxies were significantly smaller and less massive. This aligns perfectly with the scientific model accepted by experts. The density of matter in the early universe was simply insufficient to create galaxies the size of those observed today. What began as the identification of 6 glowing red-shifted spots from the James Webb Telescope has triggered one of the most significant cosmic mysteries in recent years. Although these newfound systems are similar in age to more recently recorded ones, they are generally as large as our own Milky Way. This has created a fascinating mystery. Later, after examining a series of images captured by the near-infrared camera, experts identified the aforementioned light sources. Using redshift to confirm that the light from these objects took over 1 billion years to reach our eyes on Earth, it was determined that these structures existed around 570 million years after the Big Bang. By analyzing the characteristics of these systems, it was concluded that the Webb telescope had captured 6 early galaxies in its photos. Astonishingly, these galaxies were so massive that they challenged typical cosmological theories. Instead of finding the usual smaller galaxies, structures were identified that were nearly as massive as our Milky Way, despite forming early in the universe's history. If we continue to analyze the data collected by the James Webb Telescope, this gravitationally bound collection of stars was already more than 10 billion times the mass of the Sun at that time, with one possibly surpassing 10 billion solar masses. However, whether this scenario is accepted remains uncertain. For instance, there would have been significantly more mass in the early universe than previously estimated, which presents a problem. The identified objects challenge virtually all traditional cosmological theories. If even one of these colossal galaxies turns out to be real, it would contradict our prior assumptions. Additionally, the density of matter in the early universe would need to be several times greater than previously predicted to account for this anomaly. Another equally bizarre explanation depends heavily on how these grand systems formed, something that remains completely unknown to us. These discoveries and the discussions surrounding the Big Bang have prompted some scientists to diverge from this hypothesis. Various astrophysicists with alternative views feel their opinions are not being heard in scientific journals. Indeed, even those who express doubts about existing theories are often labeled as outlandish. However, it's clear that even experts who still advocate for the Big Bang theory are continually confronted with questions that require convincing answers. These questions include specific issues like why and how, 13.8 billion years ago, something emerged from nothing. Could something ever truly begin from nothing? Was there some triggering event, or was it all a coincidence? Steven Weinberg pointed out that the concept of time as we understand it began solely with the Big Bang. Therefore, this process could not have been triggered by something beyond it. A similarly puzzling question relates to the consistency of radiation and density throughout the universe. No matter which direction we look or at what distance on a larger scale, we find similar densities and distributions of galaxies, nebulae, and radiation. Experts attempt to explain this phenomenon. Peculiarity through the hypothesis of expansion. Anyway, a few experts take this supposition further with a hypothesis of wild expansion. As per this thought, expansion has only halted in specific regions, like air pockets, and continues endlessly elsewhere. This suggests that different universes could be forming in these air pockets, each with its own unique physical laws. In this model, a key question arises. What if our universe doesn't represent the entire picture? More intriguingly, consider the possibility that another universe existed before our own. For this situation, the Big Bang would become part of a larger cycle. According to this view, our universe is part of a greater multiverse. Within this framework, the possibility of an eternal cycle of death and resurrection of universes is advanced. However, this isn't the only perspective presented in the field of cosmology. In 1955, for example, an article appeared in NASA's Spacetimes, arguing that there may have never been a Big Bang, as the universe has existed for an infinite amount of time. In this view, the expansion of the universe would be non-existent, and the observed structure of matter could reflect steady-state conditions. Moreover, another fascinating theory arises from the realm of quantum physics and string theory. Several experiments have suggested that our universe and everything in it could simply be a flat, three-dimensional image projected onto a surface. Consequently, there is a potential idea that our reality is the result of a higher-level simulation. While this might sound like the plot of a sci-fi movie, it could be connected to the Kardashev scale, which measures the level of advancement of a civilization based on its ability to harness energy. Assuming there were a Type 3 civilization capable of fully utilizing the energy of an entire universe, it might have created a grand simulation. Getting this right in such a scenario is a genuinely complex matter. Exploring the depths of cosmology and the origins of our universe leads us into a realm of great mystery and ongoing scientific inquiry. The new images captured by the James Webb Space Telescope have reignited debates about the true nature of our reality, challenging established theories and prompting researchers to rethink fundamental aspects of cosmological understanding. At the core of this inquiry lies the theory of how everything began, a foundation of modern cosmology. According to this hypothesis, around 13.8 billion years ago, the universe emerged from an incredibly dense and hot state, rapidly expanding and resulting in spacetime and matter as we understand them today. This grand event was not just an explosion within prior space, but may have marked the very beginning of space itself. The concept of a singularity, where gravitational forces are so intense that spacetime becomes infinite, supports our understanding of this early phase of the universe. However, the discovery of early systems by the James Webb Telescope challenges assumptions about how quickly systems formed in the universe's infancy. These systems, identified within a few 100 million years of the Big Bang, appear remarkably developed and massive, contrary to assumptions based on current cosmological models. One of the pressing questions raised by these discoveries is the nature of inflation. As proposed by the prevailing theory, inflation occurred within fractions of a second after the Big Bang, causing the universe to expand rapidly. Furthermore, this rapid expansion would explain the uniformity of the cosmic microwave background radiation observed across the universe today. However, the new discoveries suggest complexities in the early development of the universe that may require revisions to inflationary models. The formation of galaxies, like those observed by the Webb telescope, forces cosmologists to reconsider the conditions and processes governing the universe's early development. These enormous systems, now critical in size and mass, suggest a matter density that exceeds previous estimates. The mystery continues as experts contemplate how such massive structures could have formed and evolved in such a relatively short period. Additionally, the discovery of these early galaxies raises intriguing questions about the nature of dark matter and dark energy, two elusive components that make up the majority of the universe's mass and energy content. While dark matter is understood to provide the gravitational foundation for galaxy formation, the distribution and properties of dark matter in the early universe remain uncertain. In line with these astrophysical mysteries, theoretical physicists are exploring alternative cosmological models that challenge the standard Big Bang view. Some theories suggest that our universe is just one among many in a vast multiverse, each with its own distinct physical laws and constants. These ideas, emerging from advancements in string theory and quantum cosmology, propose a more complex and interconnected universe than previously imagined. One idea gaining traction is the concept of eternal inflation, where universes continuously emerge from a larger expanding space. This theory suggests that our universe might be just one bubble among countless others, each with its own unique properties. The challenge lies in finding observational evidence to support such speculative ideas, as they stretch the limits of empirical validation. Another provocative theory is that our universe exists within a simulated reality, much like a computer-generated game. This idea draws parallels with advancements in artificial intelligence and computational science, where simulations can replicate complex systems, potentially providing insights into the fundamental nature of reality. Regardless of the ultimate outcome, these discoveries prompt a shift in the way we understand the universe. The James Webb Space Telescope's findings indicate that much about the universe's early history remains shrouded in mystery, encouraging scientists to revise long-held assumptions and explore new theoretical frameworks. With all these ideas being proposed, one question is fundamental. As the universe continues to expand and evolve, will we ever truly understand its origin, or will the mysteries of the universe remain an enticing enigma? With each new discovery raising as many questions as it answers, the journey toward comprehending the universe's true nature has only just begun, and the implications for cosmology and physics are profound.